Today, we're going to decode a secret language, one that governs the entire molecular world. But it's a language written not in letters, but in shapes. We are talking about symmetry and the incredibly powerful mathematical grammar that lets us finally read it, group theory. All right, let's just jump right in with a question you've probably wondered about. Think about some of those chemicals you see in a lab, the brilliant blue of copper sulfate or that deep, intense purple of potassium permanganate. Why do they have these amazing, vivid colors when something like table salt is just, plain white? It might seem like just a random quirk of chemistry, but it's not. Not at all. There's a fundamental role at play here, a hidden principle that dictates these properties. And that principle? It's symmetry. To understand what's going on, we need to learn its language. And that language is called group theory. Now, before we get to all the cool molecules, we first have to understand the mathematical toolkit we're going to be using. So, what exactly is a group? So, in mathematics, a group is this surprisingly simple but incredibly powerful idea. It's really just a collection of things, we'll call them elements, and an operation, kind of like addition or multiplication, that combines them. But here's the key. That combination has to follow 4 very specific rules, or axioms. Let's just quickly break down these 4 rules. First up is closure. This just means if you combine any 2 things in your group, the result is also in the group. You can't escape it. Second, associativity. This means it doesn't matter how you group the operations, the result is always the same. Third, there's got to be an identity element, basically a do-nothing operation that leaves things exactly as they were. And finally, every single element has to have an inverse, a perfect undo button that gets you right back to the identity. It's a perfect, self-contained little system. Okay, so how does all this abstract math actually connect to the real world of chemistry? Let's take a look at how these rules apply to actual molecules. This is where it gets really, really cool. In chemistry, the elements of our group, they aren't numbers. They're physical actions you can perform on a molecule. We call them symmetry operations, things like rotations or reflections that you can do, and when you're done, the molecule looks completely indistinguishable from how it started. Let's take a super simple example, good old water, H2O. First, you've got the identity operation, which we call E. That's just leaving it alone. That's our do-nothing element. But you can also rotate it 180 degrees around an axis that runs right through the oxygen atom, and hey, it looks exactly the same. That's a C2 rotation. Then there are 2 different mirror planes you can reflect it through and get the same result. These 4 operations, E, C2, and the 2 reflections, they actually form a complete, perfect mathematical group. And this collection of symmetry operations for any given molecule, it has a special name, a point group. For water, we call it C2V. You can think of each point group as a unique dialect in this universal language of symmetry, and it describes with perfect precision how that molecule is built. All right, now that we have this new language, we can finally go back and solve our original mystery. How does the symmetry of a molecule actually create its color? Well, the answer comes from a concept called crystal field theory. This theory zooms in on a central metal ion and basically treats the atoms surrounding it, the ligands, as simple points of negative charge. It then shows us how the symmetrical arrangement of those charges messes with the energy levels of the metal's own electrons. And this slide shows the incredible effect. If you have a metal ion all by itself, its 5 key d orbitals all have the exact same energy. But when you surround it with other atoms in a symmetrical shape, like this octahedron here, that symmetry forces the orbitals to split. As you can see, 3 of the orbitals get pushed down to a lower energy state, while the other 2 are forced up into a higher one. So, how does this make color? Well, that energy gap is everything. When white light hits the molecule, it can absorb a photon that has the perfect amount of energy needed to kick an electron from that lower level up to the higher one. This means the molecule is literally plucking one color out of the light. Our eyes then see all the colors that are left over, which we perceive as the complementary color. So the molecule's symmetry directly creates the energy gap that dictates its color. Amazing, right? But predicting color is just the beginning. Let's look at another really powerful application. Understanding how molecules are constantly moving, vibrating, bending, and stretching. Scientists can actually see these vibrations using techniques like Raman spectroscopy. What they do, as this diagram shows, is shine a laser on a sample,
Now, most of the light just scatters back with the same energy, but a tiny, tiny fraction gets changed. It either loses or gains a bit of energy. And that exact energy difference corresponds to a specific molecular vibration. It's like the molecule is a tiny bell, and Raman spectroscopy lets us hear the exact notes it's playing.
Here's the thing, though. A molecule can't just vibrate in any old random way. It has very specific, allowed ways of moving. And even more important, not all of those movements can be detected by every technique. So how do we know which ones we can see? Yep, you guessed it. Group theory gives us the answer, and we call them selection rules.
These selection rules are different for different techniques, and they are based entirely on symmetry. For a vibration to show up in an infrared or IR spectrum, the motion has to change the molecule's overall dipole moment. But to be seen in a Raman spectrum, it needs to change the molecule's polarizability, basically how easily its electron cloud can get distorted. Group theory tells us, with mathematical certainty, which vibrations do which. And this is so powerful because it means a chemist can predict the spectrum of a molecule they haven't even made yet just by knowing its shape.
So, as we're seeing, this isn't just some niche mathematical party trick. Symmetry is a universal organizing principle that unlocks a much deeper understanding of, well, all of chemistry.
The applications go way, way beyond just color and vibrations. I mean, group theory is essential for building molecular orbital diagrams, which explain chemical bonding itself. It's the basis for the rules that tell us if certain chemical reactions can even happen or not. It lets us predict chirality, a property that's absolutely crucial in designing drugs. And it's fundamental to crystallography, the study of how all atoms arrange themselves in solids. It's everywhere. There's this quote that just hits the nail on the head. It says that groups share a fundamental kinship with the idea of symmetry. And that's the perfect word for it. The mathematical structure of a group and the physical reality of symmetry, they aren't just related, they're family. They are two sides of the same coin, one abstract, one physical, that together give us this unbelievably powerful framework for describing our world. So, we've seen how symmetry dictates the rules for how molecules behave, from their color to their vibrations to their very ability to react. It's a hidden language that, once you learn to read it, reveals this beautiful, deeper layer of order, which really makes you wonder, what other hidden rules is this same principle of symmetry writing for the rest of our universe?